And we're back to talk more about atomic spectra. Okay, so last time we introduced the energy level diagrams here. We have one for hydrogen, we have one for mercury, and we're kind of going over how the different features of that relate to both the Bohr model, which was the basis for kind of all of the spectra that we look at now, and also the current cloud model, which just describes it a little bit better than the Bohr model in most cases. We said yesterday that electrons inhabit or are in typically these different energy levels. For hydrogen, it's n equals 1, 2, 3, 4, 5, 6, and so on and so forth. And for mercury, we just label them with letters A through J for our diagram's purpose. An electron doesn't have to stay in its energy level. It can move up or down energy levels. When it moves up an energy level, it has to absorb a photon in order to do that. Remember, a photon is just a light particle, and light carries energy with it. So when an electron absorbs a photon, its energy increases and it goes up to another energy level, possibly. The photon that it absorbs has to be the exact right amount to move up, or else nothing will happen. Electrons have to be in these certain energy levels. They can't hang out in between. They have to be exactly in those different energy levels. So, when an electron is in orbit around an atom, we typically say that it has negative energy, and you can see that based on the energy off on the right-hand side of these diagrams. You can see for n equals 1 for hydrogen, it's negative 13.6 eV. Remember, eV is electron volts. For n equals 2, it's negative 3.4. For n equals 3, negative 1.51, and so on and so forth. It's the same thing for mercury. The reason we say that it has negative energy is that negative really just tells us that the electron right now is bound to that atom. Something that is bound, typically we say it has negative energy. It can't go wherever it wants. It has to stay in orbit around that, whatever it's bound to. So in this case, the electrons are bound to their atom. It is not completely free to move because it has to stay close to that nucleus. Remember, they're attracted to the nucleus. Electrons are negative, nuclei are positive. So that's why it's bound. There's an electrostatic force there that causes it to stay close to it. However, what happens if you give the electron more and more energy? The energy becomes less and less negative. If you were to give this, let's say, 10.2 electron volts, now it's in that second energy level, and it has the energy is a lot less negative, if that makes sense. So in other words, if you can keep doing this, if you allow an electron to absorb enough energy to make its energy either zero or even positive, that is what happens when we have ionization. It will ionize and just simply leave the atom behind. Now it has positive energy. It is no longer bound. It doesn't have to stay near that nucleus. It has enough energy to escape. The more positive energy you give it, the faster that electron will move. So any leftover energy simply becomes the energy of motion, that is, kinetic energy. Now, it doesn't have to do that. Not every atom will ionize. When an atom returns to a lower energy state, instead of absorbing a photon, this time it emits or gives off a photon. It gives off that energy, because remember, photons carry energy with them. And that photon will have a certain energy and a certain frequency. And since the electron has to go between energy levels, it's very predictable what the energy that it gives off will be. For instance, if you have an electron moving from n equals 2 down to n equals 1, the energy of the photon that it gives off will be 10.2 electron volts, because that's the difference in energy level right there. So to determine the energy of this photon, all you do is you find the difference in energy between, and be very careful how you write this, the initial and final energy levels. Notice I didn't say between final and initial. I said between initial and final energy levels. This is the only time in this class that we are going to use do something that's initial minus final. So, I'm going to ask you to turn in your reference tables to page 5. And we're going to write out an equation. For emitted photons, the energy of the photon is equal to EI minus EF. And that is right in the reference tables. It's the second equation down on the modern physics page. Okay, right there. E photon equals EI minus EF. Now that's for when photons are getting emitted. If you want to find the energy of a photon that was absorbed, then you do EF minus EI. Now, why is everything kind of switched up for this? The reason everything's switched up is because of this negative that we say the negative energy that we say the electrons have when they're bound, okay? That's why we have to kind of reverse everything. But the most important thing, to find out the energy of an emitted photon when an electron moves from one energy level down to another energy level, we take the initial energy level where it started, subtract from that the energy level where it finished up, okay? One mistake that I see people making with this all the time is they assume that, how should I put this? They assume that these energy levels, they don't think about the difference between energy level. They think that just, let's say, a 3.4 electron volt photon can be accepted and can always be accepted and can cause an electron to move up in energy level. Well, that might work if it's on the n equals 2 level, but that's not going to work down here because it's all about the difference between energy levels. If a 3.4 electron volt photon hit an electron that's in the ground state, that wouldn't do anything because there is no energy level that's exactly 3.4 electron volts above this energy level. Okay, so again, it's not about necessarily the numbers of these energy levels, it's about the differences between the numbers of the energy levels. Okay, and that's kind of tough to understand at first. All right, we're getting close to being able to do some examples, which is good because the examples are a little bit more mathematically involved, but it's honestly kind of fun to see how they work. So, to find the energy, we take the difference in energy level. If we then want to find the frequency or wavelength of the photon, then we use the equation that we talked about a few days ago. We use this equation right here. E photon equals HF or equals H times C over lambda. A couple notes with this. E for this must be in joules. Why is that? It's because, well, remember what H is? H is Planck's constant. And Planck's constant is given on the front of the reference tables. And the way it's given on the front of the reference tables, unfortunately, is not in electron volt seconds. It's in joules times seconds. Right there, you can see it. So since Planck's constant references joules, the energy has to be in joules as well. Okay. So why do we want to find the frequency? Why do we want to find the wavelength? Why do we want to find the energy? Why do we want to do any of this? Remember, each element has its own very specific set of energy levels. So what that means is each element, when you have electrons that are coming back down from higher energy levels to lower energy levels, emits very specific, a unique set of photons with a unique set of energies. And since the energies are all different for different elements, that means that the frequencies of light that they emit are all going to be different. So you can characterize an element by what frequencies of light it emits when the electrons are excited and they fall back down. And how do we interpret frequencies? We see frequencies as colors. So we can identify these elements by what colors of light are coming off of them as their electrons become de-excited. And we use these sets of frequencies, they're known as emission spectra, to determine what types of elements are present in a sample. Okay? We can actually find out. We can take a piece of something, we can excite the electrons, and we can see, based on the light that they then give off as they fall back down, okay, well, what is in this sample? What types of elements? What types of ions are in the sample? What types of molecules are in this sample? So this principle is really, really important. You use this in many, many, many different places. We use this to, so quite obviously what I just said, determining what elements are present in a sample. We use emission spectra to determine what a star is made out of. Astronomers use this often. And we actually use this many, many different times in the medical field. I'm not going to get into all of them, but this is the principle behind how we see what certain tissues and different things in your body are made up of. And there's many, many uses of that. Many, very many medical techniques. And before we get to the examples, I just want to talk about one other sort of related thing. You can also kind of do the reverse of an emission spectra. There's also something that you should know about that is called an absorption spectra. I know I'm kind of cramming a lot of writing in here, so I apologize. And I spelled spectra wrong. So there are also something called an absorption spectra, where you take white light. White light obviously is made up of all the different colors. If you combine all the different colors together, it's not black light, it's white light. And you pass that through some sort of what's called an elemental gas. In other words, a gas that is just made up of one element. So what will happen if you pass white light through this elemental gas, that gas contains atoms, which contain electrons, which when the light hits it, some of those photons are exactly in the right, or have exactly the right amount of energy to excite those atoms. So those atoms will absorb that light and then move up in energy level. Well, if the atoms absorb that light, they're then eventually going to re-emit it, but not in the same direction that the white light was originally coming in from. So they'll re-emit it in a different direction. So imagine if you are standing on one side, you have a white light source on the other side, and then the gas is in the middle. If the gas wasn't there, you would see the white light. You would see all the different colors and frequencies, in the spectrum. However, once you put the gas in the middle, now you're not going to see those frequencies of light, those photons that have the right energy that get absorbed up out of the spectrum. So what you'll see is not quite white light. You'll see a spectra if you graph all the frequencies with some of the frequencies removed. Okay, so some of the frequencies of light get absorbed depending on what the gas is. And that leaves essentially some dark spots. So dark spots are fringes. I'll just go dark spots in the spectrum. So or dark lines really. So an emission spectrum is dark, but you see certain lines that indicate, okay, here is one of these. Here is one type of photon, or a photon of a certain frequency that's getting emitted because of this energy level transition. Okay, and everything else is dark because those photons don't exist because those energy level transitions don't exist. For a absorption spectra, it's the opposite. All the frequencies of light are there. The only ones that aren't correspond to the energies, or correspond to photons whose energies made them get absorbed by the gas, and then the light gets scattered out. Okay, so an absorption spectrum can also help determine the presence of elements. It's just kind of like the exact opposite of an emission spectrum. All right, let's get to some examples. So what we're going to do, we'll do a couple of them here, and then we'll finish the video. We're going to determine the energy and frequency of the photons given off by electrons, and we're also going to determine, the type of radiation. So whether it's a radio wave, FM wave, etc., given off by electrons that make the following energy level transitions. And this is a very repeatable process. Essentially, there are really like three and a half steps to this, okay? And it's the same every single time. So for the first one, we want hydrogen Let's say that we have an electron in hydrogen, and it goes from the n equals 3 state down to the n equals 1 state. Well, n equals 3 corresponds to an energy level of negative 1.51. N equals 1 corresponds to an energy level of negative 13.6. So the first thing we need to do is we need to figure out the energy difference between these levels, because that must be the size of that must be the amount of energy emitted with that photon. That's how much energy that photon is carrying. So we use this equation. E photon equals EI minus EF, energy initial minus energy final. E photon, we just said it's negative 1.51 eV minus a negative 13.6 eV. So the energy of that photon that gets emitted, and it is important, make sure you know how to use the negative on there. So negative 1.51 minus negative 13.6. The energy of the photon that got emitted, based on the difference in energy levels, is 12.09 electron volts. So, remember, we said that in order to find the frequency, we use this equation, but the energy must be in joules. We need to convert this. 12.09 electron volts needs to get converted to joules. If we set up the unit conversion fraction, that means EV is going to be on the bottom, joules is going to be on the top. On the front page of the reference tables, we see that the conversion between 1 electron volt equals 1.6 times 10 to the negative 19th joules. So we need to take 12.09 electron volts multiplied by 1.6 times 10 to the negative 19th joules, and we get 1.9344 times 10 to the negative 18th joules for the energy of that photon that got emitted. Then, all we have to do now, we now have this in joules, we just have to figure out the frequency. E photon equals HF. The energy of the photon is 1.9344 times 10 to the negative 18th joules equals H, Planck's constant, is 6.63 times 10 to the negative 34th joules times seconds. We simply take what we just got for the energy of the photon in joules, divide by Planck's constant, and we get the frequency of, in this case, 2.92 times 10 to the 15th. If we want to know what type of radiation that is, it's always good that we know the frequency. We never want to do this with the wavelength. That can get a little misleading. If we want to know what type of radiation this is, we go to the electromagnetic spectrum, and we look, and we see that it's, okay, so 2.92 times 10 to the 15th hertz, that's clearly above the upper limit for violet. So what comes after violet? That would be ultraviolet. And that's the range from 10 to the 15th all the way up to 10 to the 18th. So X-ray doesn't even start till 10 to the 16th, so it can't be X-ray. This must be ultraviolet light. So what this means is when a hydrogen atom has an electron that goes from n equals 3 down to n equals 1, it will emit ultraviolet light. That is the telltale type of radiation that shows that, hey, we have an electron in a hydrogen atom transitioning from n equals 3 to n equals 1. If you see light with this frequency, that's where it came from. Let's do one more real quick. Hopefully it won't get cut off. It's the same exact basic process. Hydrogen n equals 5 to n equals 2. N equals 5, you got to be very careful reading these. N equals 5 is negative 0.54. N equals 2 is negative 3.40. So E photon equals EI minus EF. What did I say? Negative 0.54 EV minus a negative 0.34 EV. Okay. That comes out to 2.86 EV. We have to convert that. 1 eV is equal to 1.6 times 10 to the negative 19th joules. And that would be 4.576 times 10 to the negative 19th joules. And then we simply find the frequency. Oh. Messed it up. The frequency is 6.9 times 10 to the 14th hertz. We look at our spectrum table. 6.9 times 10 to the 14th falls between 6.59 times 10 to the 14th and 7.69 times 10 to the 14th. These are the limits for violet, by the way. It doesn't mean violet is this. This is the lower limit for what we call violet. This is the upper limit. So 6.9 falls between those two. That means that this must be violet light.